Huge round of applause for Adrian Mouat, please.
Okay, so I'm going to give a talk on container orchestration. I'm going to cover Kubernetes, Docker Swarm, a Mesos-Marathon. There was going to be Nomad as well, but unfortunately, it was going to make it a really long talk. Was the main problem. Before I get started, who uses Kubernetes? Okay, a few of you. Does anybody use it in production? Oh, cool. One, maybe two. Probably Docker Swarm. Does anybody use Docker Swarm? Okay, a few. And does anybody use it in production? No, I don't think so. Although somebody is telling me about it in production next week. But Mesos-Marathon. A few more, and I bet you are using it in production, are you? Yeah, see? Okay, that's interesting. Right. Okay, so what is orchestration? Does anybody want to try and define orchestration for me?
Which context?
Well, container orchestration. Or you can talk about an orchestra, because I mean, it actually has a lot of
Harmony.
analogies.
Exactly.
Harmony, okay, so things working in harmony. That's probably not bad.
Well, it's basically going from one single container to multiple containers and trying to link them all together, you know, like a symphony orchestra, like there's the bass players, the networking, the storage, being the trombone. Give the mic.
Yeah. Do you want to, I'll tell you what, you can just come up here. No, that was very good, thank you. I've cheated, I went to the Oxford English Dictionary. So, one definition of orchestration, and the one that's relevant in this context, is the planning or coordination of the elements of a situation to produce the desired effect, especially surreptitiously. I like the especially surreptitiously bit.
What does that mean?
What does it mean? Shh, don't spoil it. So, the first thing there is elements of a situation. So, if you're thinking about container orchestration, I'm going to argue that our elements are containers, the things you're actually running, the hosts they run on, and as you were saying a minute ago, how you network them all together and get them to work together. The next bit was to produce a desired effect. I'm going to claim that this desired effect is essentially to have a running application, right? But not just that. Ideally, it should automatically scale, so you get more load. It starts with more containers and they're all correctly networked, etc. It should be fault tolerant, so if a host or a container fails, it should start up a new one and fail over automatically. There should be health checks, rebalancing. It should use resources efficiently, so it should make maximum use of my hosts. Save me money, hopefully. And what I think is really meant by the especially surreptitiously bit in this context is it should require little manual intervention, right? I think it should happen automatically, so without you noticing to a certain extent, which is what surreptitiously means in case you're wondering. But is it important? So why would you want orchestration? And if you're running like small stuff on your laptop or you're only running 2 or 3 containers, well, chances are you don't need orchestration and it just add extra complexity. But if you're not using an orchestrator like Kubernetes or whatever, you're really doing the orchestration yourself. So you're responsible for selecting what host it runs on, you're responsible for networking it together, you're responsible for scaling it. And once you get past a few containers, and certainly once you get past more than 1 or 2 hosts, then you're going to need an orchestration framework. Okay, so throughout this examples, I'm going to use an example app. And it's a very noddy little example. It's actually very similar to the one that's in the book. What happens is, you get a web page sort of like this. Of course, it's a monitor, so my pointer doesn't work. That's quicker, wasn't it? So the name is the host name of the container it's running on, and it generates an identicon, in this case like an 8-bit monster based on that host name. And you always get the same picture for the same host name. So when different containers will have different pictures. Sorry? Thanks. It took me actually it took me longer than it should have. Anyway. it's composed of 3 services. There's the main application, which I call Identi-Orca. There's an Identicon server that I got off some French guy. That's called DN Monster. And there's also a Redis container that's used to do cache. Okay, so the first one we're going to see is a swarm. I'll also talk a little bit about Compose. So this is like Docker's official solution. The interesting thing is that Swarm uses the same API as the main Docker engine. So when you do Docker run, you still do Docker run against Swarm. It's exactly the same calls, except Swarm will then decide which host to run that container on. So it works almost identically to how it works on a single host. Arguably, Swarm is responsible for clustering, as in making a group of resources appear as a single resource, whereas Compose is responsible for the orchestration, as in like saying how you connect things and how to scale things up, etc. So I start with Swarm. The main reason I start with Swarm is that it's a little bit simpler, so I can sort of get across a couple of the concepts that are common to all orchestration frameworks. So the first one is scheduling. And this is basically how do you select which host to run a container on. There's 2 main things, strategies, so how you select the host, and also filters and constraints, which allow you to say things like, put it next to this container or on a certain host, etc. So in Swarm, there are several scheduling strategies. There's random, which is pretty much useless and just for testing, where it picks a random host to start a container. There's bin pack, where it attempts to completely fill a host with containers before it moves on to the next host, or more or less. And then there's spread, where it attempts to spread the containers evenly across all hosts. Those 2 are sort of contrasted because in bin pack you make a very efficient use of your resources, but if one of those hosts was to go down, you're going to lose a lot more than if you're using spread. Because if you're on the spread strategy, there's less around each host, right?
Depends. If it's a host which is not filled at all.
Yeah, right. But potentially you could lose everything in bin pack, right? Yeah. What you said was potentially on bin pack, if an empty host goes down, you lose nothing.
Whoa. Sorry.
Well, that's a fair point, I don't know. The other thing about bin pack is if you have some large containers that you want to run that use a lot of resources, what you might find is if you're on the spread strategy, no host has enough spare capacity to run it. But if you're in bin pack, there'll probably be a large chunk of free space in one of the hosts. So those are 2 sort of competing schedulers. Docker also talk about being pluggable. There is interfaces and so on if you go and look in the repo, but there doesn't seem to have been that much made of it so far. There is the idea that we'll be able to run Swarm on top of Mesos and Kubernetes and so on. And I think that's what they mean by pluggable. And also, obviously, they just acquired a team that's working with Apache Aurora, which is a Mesos scheduler, so I guess we'll see more coming out here. And filters. So these essentially constrain which node a container can be scheduled on. So for example, you can say something that only start on a node that's been labeled staging, or only start the container on a node which already has pulled the image. So the advantage of that one is if a container's already pulled the image, clearly it's going to start up quicker than it has to go up to a registry and pull the image. And you can have hard and soft constraints. So you can say, okay, prefer a node where it's got the image already pulled, but if none exists, go and pull the image. Another common one is to schedule a container next to an already running container. To say these two containers should always be on the same host. Okay, the demos. Yeah, I'm afraid they are videos. There was no way I was going to do 3 separate demos all live, and they're all quite complicated. Okay, so I did this on DigitalOcean using Docker Machine. So I've got like 2 nodes set up in DigitalOcean. You type Docker info. So if you were to run like Docker info against a normal Docker engine, it looks a little bit different. But if you run it against a Swarm cluster, you get something like this. And so you can see that a bit more information on the cluster. It's using the spread strategy, which is the default one. You get a bit of information on the nodes. So you can see it's got 2 nodes. We can also see it's got a few containers already running, which I'll explain now. So if we do Docker PS, we can see Well, actually, it doesn't matter. Basically, there's a few containers that are running, and they're just to do with like some like infrastructure stuff that we'll come back to later. Okay, so the actual application so this is the compose file for the application. You can see the three services: Adenta Orca, DN Monster, and Redis. We'll do this environment stuff later. The Adenta Orca one depends on DN Monster and Redis. Technically, you don't actually need to depend on. And this is the only one that exposes a port, because that's the one that people connect to. There's a hole behind me. Yeah, and it's the problem with doing videos that they never go on when you want them to. So there's a port there.
Wow.
I can't spell Docker. Okay, so we're starting up the application, creates a network, brings up the services. This is actually all in real time, which is quite cool. I do Docker PS, two things here. If you dash n equal to 3, it gives you like the last 3 containers that were started. The other thing I should point out is I've got a slightly, I've edited, oh, it's right down the bottom. I've edited PS, so, does that work? Oh, it actually works, man. I thought it was some sort of practical joke where you shake it and it starts working again. Okay, so I've edited PS, so that's why I'm only getting like 4 headings, so it fit in the screen. But basically you can see our 3 things running there. One thing I would like to point out though is it does give you like the names of the host that it's running on. So here we can see the Adenta Orca container started on the node swarm 1, and the Redis container started on master, and the DN Monster container started on swarm 1 as well. Okay, and to connect to it, we've got to ask which port it gave to the Adenta Orca container. Yeah, and so we can just grab that and go to it, and hopefully this will come up. Well, I'm saying hopefully, it's a video, it will. Oh, it'll be a very bad video. Yeah, so there's the application running, and that's on DigitalOcean. Yeah, it's assigned an ID. That ID gets turned into that image. There's also a version of sound that I cropped it from. I probably should have just done that version separately. So if we go back to Docker Compose YAML, the next thing I want to show you is the environment stuff. So the constraints. So if I put this, so you specify constraints by setting environment variables on containers. And here I'm saying the affinity, setting a container affinity. So I'm saying I want the Redis container to come up next to this container, Adenta Orca DN Monster, which is the DN Monster container. So if we save that, and we come out, we take this whole thing down again, and restart it. And now hopefully the DN Monster and Redis containers should be started on the same host. And that's basically like affinities for you. And all the orchestrators essentially a way of doing this. So yeah, you can see there's the Redis containers in Swarm 1, and so is the DN Monster container this time. If it had been unable to meet that constraint, you would have actually got an error in the Docker Compose up path. Okay, and now a bit more interesting, what we want to scale the application. So in this case, all we're going to do is try and scale the Adenta Orca service, and we're going to start the 9 extra instances of it. So we're going to scale it up to 10 instances. And this is pretty simple and it's pretty fast. It's pretty impressive that it starts like 9 containers in a few seconds. But it's also arguably, a little bit useless because it started 9 containers. But the problem is I don't have any way, I can go and connect them individually, but that's not what you want. You really want to like load balance over them. And the thing is, Swarm doesn't really give you a way to do that. You've got to go through third-party tools. So one way to do this, and possibly the most common way, is to use something like Registrator from Glider Labs, and that will monitor the Docker event stream. And whenever a container comes up, it'll go and save it into console or whatever. And then you can do something like use the console template to update a proxy of the container that's come up and have that, do your load balancing for you. And that works. I kind of feel it's a bit overcomplicated and a little bit hacky. So in this case, what I'm going to do is I'm going to use Flux. And Flux is like a fairly new product from Weave. We heard a little bit about earlier. They do a networking solution. Actually, in this DigitalOcean cluster, I'm just using the Docker overlay networking. I'm not using Weave networking, I'm just using Flux from Weave. Flux, I think, is described as a service routing layer. It's essentially like a proxy load balancer. So it starts like the Flux balancer container on each node, and also a Flux agent, and stores state in etcd. So the first thing we do with Flux, so to interact with Flux, I'm going to use this fluxctl command, but that's really just doing calling out to this Weaveworks fluxctl container. It also has the address of etcd that I've set up previously. You want info. I've not set up anything, so it doesn't return anything. So we want to create a service for Identa Orca, and this is kind of interesting because the service is sort of, I don't know if abstract's the wrong idea. It doesn't correspond to like a concrete container or anything. It's basically that we're going to define a floating IP address, and it'll use IP tables to route things to this. Obviously, you have to choose an address that isn't being used in the network, but I know that space is free on this network. It can be actually any address you'd like as long as it's free. The -- protocol HTTP bit, it's just for metrics. So that's set up the service. Now I need to set up a rule for the service, which basically tells Flux which containers are going to back the service. So when it gets a request on that service, where they should go. And what I'm saying is that you're going to have a default rule, and it'll route to any container that's built from the image amod/Identa Orca. And the port it should route to is the one that was mapped from 1990. So I'll actually go into Docker and ask it which port 1990 maps to in the host. And that's it working already, but it's only working in the network space, so and the sort of Docker space, if you like. So we're going to run a Docker container and connect to that IP address, and we should get a response. Yep. And you'll note that's A663. If we do it again, should be a different node, because it just round robins around the nodes. Great, so that's working. But we're still not there, because it's still not exposed to the external world. So the final step is to have what Flux calls an edge balancer, which I think is actually just a modified version of Nginx. And that's basically just going to route to the Identa Orca service on port 80. Okay, and again, we've got to run Docker port to figure out where it's running. So we can see it started in Swarm 1. And if we go to that address, but now we've got our 10 instances being load balanced across there, which is quite nice.
Only work with T-service
no, I think it's fine. That's just what the protocol HTTP bit is just for metrics. It also integrates with Prometheus, so you can get all the metrics and what's going on in your containers. Yeah, so that's pretty much Swarm. There's a few gotchas. You need third-party tools. Rebalancing is still experimental, so if something goes down, it's not going to restart the container somewhere else for you unless you use the experimental version, and even then it's a little bit, it's still being worked on. And also master replication is experimental, so it's hard to run in a sort of highly available mode. I'm not sure I like the fact that it overloads the Docker API. So, for example, if you're using binpack, you have to specify the amount of CPU and the amount of memory that a container has. And you do that by just using -c CPU and assign CPU and so on. But that's kind of different to how it works with a normal Docker engine, right? So in a normal Docker engine, if you specify -c and CPU, that's actually a constraint that says this container can take it as much of that. It's not a hint to a scheduler. So I'm not sure I like to overload the API. The other thing is there's no pod concept, and so there's no way you can say these two containers should always be scheduled together or not at all. So although we saw an example earlier where I scheduled two containers in the same host, they weren't scheduled at the same time, right? One was scheduled, and then it tried to schedule the next one next to it. But I can't say schedule them both or neither, if that makes any sense. So in conclusion, Swarm works. You've got to use it in conjunction with other software such as Weave, Flux, The big advantage is really simple. You can just do Docker run and get things running, but that's also kind of the disadvantage in that it's harder to do more complicated things. So the next one is Mesos, or more accurately Mesos and Marathon, Marathon being the framework. This one's the only orchestrator that actually sort of predates Docker, if you like. It's used by a few large companies, which is, I guess, one of the main reasons you want to look at it, which is Twitter, Airbnb, and eBay. It can also run like mixed loads, so you can have like Hadoop jobs and Spark jobs running next to your Docker stuff. It's been shown to be truly scalable, so you've got Mesos clusters out there that are running on tens of thousands of nodes. There's a few core components. Yeah, I should go through that. Agents, it's made up of like Mesos agents from the nodes, Mesos master, and Zookeeper for state, and then this idea of frameworks, which is a little bit odd, but basically you've got to run frameworks to schedule jobs onto agents. So agents run on nodes and are actually things that run on the nodes that are responsible for executing tasks on the node. They also submit available resources to the master. So they'll go and tell the Swarm master, the Mesos master, I have X amount of CPU free, I've got X amount of memory free. The Mesos master will be responsible for sending tasks, in our case Docker containers, to agents, and it also offers resources to frameworks. So the agents tell the master how much resources they have, and the frameworks sort of bid on the resources. It uses Zookeeper. It uses Zookeeper to store state, which is a sort of distributed, highly available database. And one of its main jobs is just to keep track of who the current master is. So Mesos is generally running sort of a highly available setup. So you have multiple masters, one of which is elected leader, and if something goes wrong, then another one takes over. Yeah, it's quorum, and yeah, you can look up if you're interested. Frameworks are coordinated with the master to schedule tasks onto agents. There's multiple frameworks available. The one we're going to look at is Marathon. You can run multiple frameworks in the same Mesos cluster. There's other ones like Aurora, Kronos, which is sort of cron for the data center, and Elasticsearch, which will run an Elasticsearch cluster for you. It looks kind of like this. So you've got Zookeeper storing state, Marathon. If you can't figure it out already, it's called Marathon because it's responsible for long-running tasks. Boom, boom. You have the Mesos master, which is scheduling jobs onto the Mesos agents. Demo. Okay, so in this case, I've just run a few virtual machines on my home desktop. So we can see there's 3 machines running there. The first thing we're going to do is set up Mesos DNS. So this is going to allow us to refer to containers by name. There's a few things in here. So when you want to upload jobs to Mesos, you've got to create this DNS.json, well, not DNS, a JSON file describing the task. It's kind of analogous to like your compose YAML again. So we set up an ID with a name. In this case, we've got using Docker as our containerizer. There are other things you can use. We're using this Mesos DNS image. We want to set it in the host network, which is the same as doing -- net equal to host. And we've got a few environment variables that are setting up, the address of Zookeeper, etc. We also have to tell it how much resources it needs. So how much CPU, how much memory, how many instances. In this case, only one. And also note we've got this constraint here. I've told it I want to start on this node, which is actually the same node as the Mesos master. So I'm going to submit it just by curling that JSON file to the master. There is also a Marathon CTL you could use, which is a little bit simpler, but I just kind of want to show how it works. I should sped up the typing bit. Okay. So it's accepted that, and that's now running. And this is the UI for Marathon. So you can see Mesos DNS is already up and running. Next thing we do is set up the Redis container. So this is pretty simple. We are mapping a port, and we're using the bridge network. Again, we've got CPUs, memory, and instances. We've curled that. And the DN monster container, almost identical to the last one, the Redis one. Okay, and that's most up and running. There's just the Identa Orca one left, and you can see it's running there. Okay, so I think the Identa Orca one is a little bit different. Not a lot different, but yeah, I've set instances here to 5. I'm not quite sure why I chose 5. Also note, I haven't specified a host port. I couldn't really specify host port because obviously if 2 containers come up on the same node, and they would conflict over the host port, if you see what I mean. So I have to let Mesos choose a host port. Okay, so that's Identa Orca running. But again, as with Swarm, we now have the issue, okay, I've got 5 instances running, but how do we load balance over all of them? I think I pick one here just to test it out. I know. So the other thing you can do is you can ask Identa Orca about its state. So if we curl the Marathon interface for apps with Identa Orca, we get some information on the sort of running application. So here we can see the 5 instances that are running, and if we pick a random instance, and it'll give us the host IP that's running on, and it also gives us the port that's running on. So if I curl that, and that's the appropriate port, which is 16330, but I forget it here, I have to go back up, then you get a response. But as I was saying, what you really want to do is to be able to load balance over those. And for that, we're going to use the traffic proxy. And I set up traffic before, so you can see the traffic's quite nice for Marathon because it has a backend that automatically integrates Marathon. So it's actually automatically picked up my Identa Orca instances. Actually, there's also, I forgot to mention, in the Identa Orca things, I did set a label to tell it to be picked up in Marathon. I think it said traffic enable equals to true. And so traffic went and picked it up and added all those containers to load balance group. And I've independently set up this route inside traffic. And so now if I visit identa.orca.marathon with Mesos, it should route it correctly. I just hacked this by adding that name to etc hosts. But yeah, if we visit that, we're now being load balanced over those 5 nodes. So we've got pretty much the same thing running in Swarm, running in Mesos. Carlos?
What happens if your container is exposing more than one port?
Oh, which one does it choose?
Yeah.
So that's to do with, I think there probably is some support in traffic and Marathon for that. I couldn't tell you exactly. You have to look it up. It's a good question. But yeah, as you saw in Flux, you had to pick the port that you wanted that was mapped in the container. I'm not quite sure how you do it in Marathon. Yeah, so in conclusion, Mesos is pretty powerful and scalable. Probably the reason that you want to look at it most is it's kind of battle tested, right? It's been used by a lot of large companies, but you still need a bunch of third-party tools like traffic to get it to work properly. And one thing that I don't really like is the Marathon interface. I find it feels a little bit hacky, especially if you want to do things like use volumes, use a registry. It could certainly be more Docker-friendly in my view. Okay, last one, Kubernetes. Kubernetes is basically based on Docker's experience running containers, because they've been running containers for like a decade or something, and they've had like Borg is their internal one. So Kubernetes is a bit different because it bakes in a lot of the features that you've been talking about, such as load balancing and scaling and volume and secret management. It comes with them just there. However, it does mean it's got a bunch of extra concepts you need to understand, and it is comparatively opinionated. The core concepts are pods, the networking space, labels, services, and replication controllers. I'm going to talk about replication controllers here. It is actually changing at the minute. So replication controllers are going to become replication sets, and bits that will move to deployment configs. But we're going to see replication controllers. Pods are groups of containers that are scheduled together. So they're the sort of atomic unit within Kubernetes. You don't schedule a single container, you schedule a pod. And containers within a pod will share an IP address. So if you have like several containers within your pod and you want to communicate with each other, they don't have their own IP address. So what you have to do is coordinate over like local ports on localhost. if that makes sense. And single container pods are very common. And the other thing to remember is pods are considered ephemeral. You know, in the Kubernetes world, it expects them to die and reappear. The other thing is, there's a flat networking space. So any pod can see any other pod and talk to it. They all exist within the same subnet, which makes cross-host communication pretty simple. Labels. So these are just key value pairs that are attached to objects, principally pods. So you can say things like tag pods with things like version dev, front end, etc. And labels are used by selectors to identify groups of pods, etc. And used for load balance is the primary reason. Services, this works a lot like how you saw Flux in the Swarm example, just like a stable endpoint that's addressed by name, and it will forward traffic to your pods. The pods that it forwards to are selected by labels, unsurprisingly, and by default you get round-robin load balancing. Replication controllers are responsible for looking after your pods, for starting them and for scaling them. They'll monitor the number of running pods, so if one disappears, it'll start up a new one, etc. And they also scale them. So if you say, I need 10 more pods, you just change the setting in the replication controller. So I ran this on the Google Cloud. I didn't set up anything at all. So this is by far the easiest demo to get to run. So you can see I've got like 3 nodes on Google, and if you run cluster info, it tells you a little bit about the services that are running. This is just the default services you get in Google Cloud. So you've got like a DNS, Heapster, which is doing metric, etc. I do get pods, there's nothing running there at the minute. So the first thing to do is to set up Redis. So if we cap the Redis controller, that's what it looks like. Replicas is how many instances you want running. So we're saying we only want a single instance running. We're going to call it Redis pod. It's going to be based on the Redis image. And it's going to be accessed on port 6379. And you start things just by doing kubectl create-f, you can give it the file. But there's an extra step in Kubernetes because we also need to define a service before anything else can access it by name. So we're going to create this Redis service now. That's pretty simple. I just like forwarding. The service is called Redis because that's what we want to be able to access it by the name Redis in the other containers. And all it's going to do is select the pod named Redis pod. In this case, it's only a single instance. And again, you just do create-f to start it. Now, if you get pods, you should see that replication controller is running. Now, if you describe replication controllers, you get a bit more information on the replication controller. And you can also describe services to get more information on the service. And I think we do DN Monster in a very similar fashion. So this should be quite quick. Using port 8080, again, one replica. The name of the replication controller is -controller, but the name of the pod is -pod. And again, we get a service. Very similar, but access by the name DN Monster, and DN Monster should forward to the DN Monster pod. Okay, finally, we get our Identity Orca service. This is we're going to start off with one replica here. We've got container port 1990. We created it. Again, create the service. The service is a little bit different. Note the type is load balancer. So Google picks us up and says, okay, you want an externally load balanced service. It should be accessed on port 80 and should go to port 1990 on the Identity Orca container. Because it's because I've asked for like an external IP essentially, this actually takes a little bit longer. I'm hoping that I cropped this next bit, maybe I didn't. So I mean, when I did this, I did it in real time. And so I did watch kubectl describe, and you can sort of see it, how long it takes for it to come up. Okay, so after a while, it does take like a minute. The load balancer comes up. Yeah, and so we can describe the service into Orca and curl that node, we get our application. So the final bit is we want to see scaling, right? And that's pretty easy. We just tell the replica controller that you want to scale to say 20 replicas. And it does it. And so we described the RC controller. You should see the nodes coming up. They've actually already all been created by the time we typed it in, which is quite fast. And unsurprisingly, if I get the right IP, we should see the application for the third and final time. And it's kind of interestingly, it gives the pods different names, or the containers different names. But yeah, we can see it's load balancing across those. So, I mean, I find it quite interesting there because Kubernetes, I didn't set this up. You know, Kubernetes is the only one where we didn't need any third-party software at all. So you can sort of see my point about Kubernetes having features baked in. This does mean that it requires understanding some new concepts, but arguably you kind of need those concepts anyway. If you're going to do things that are, load balance, that are fault tolerant, etc. It's also, unlike Mesos, it was designed from the ground up around containers and running containers. Yes, that's it for Kubernetes, but I mean, in this demo, I've talked about a very small subset of things. And if you're looking for an orchestration system in reality, there's a bunch of other things you want to start thinking about. Persistent data. So how do you actually, run databases or have volumes mapped to the appropriate host for the appropriate container, for the appropriate... This thing's annoying.
Show it away.
Maybe it's... Oh, there we go. I thought I died there. Secrets. Kubernetes is very good with secrets. It has its own way of handling secrets. Auto-scaling. So I've talked about scaling, but I did it all manually there. It's not hooked up to like metrics or anything. Multi-tenancy. So none of that, the ones that we looked at there, support having multiple tenants in your setup. You've got to look at other things such as OpenShift, which is built on top of Kubernetes for multi-tenancy. Health checks. So both Mesos and Kubernetes have support built in for health checks. With Swarm, you'd be looking at using something like Console. But I think most importantly is thinking about how you update and maintain a running cluster. So Kubernetes has a few things there about rolling updates and so on. But don't just think about how you update your images. You've also got to think about how do you update the platform. So what happens if Kubernetes needs an update? What happens if the Docker engine needs an update? Do you take nodes out of service? I don't know. So there's a bunch of things to think about. In conclusion though, I think we've seen the different schedulers do have different strengths. So like Swarm, its strength is just that it's simple. It's also flexible, but it's lacking in advanced features. And frankly, I think nearly everybody needs the features that it's lacking. Mesos-Marathon, the big advantage of that is it's battle tested and it's been proven to scale to lots of nodes. It again lacks some features, but it's not only used for Docker, you can run other things in Java stuff and Hadoop, Spark, etc. Kubernetes, frankly I like Kubernetes the most. It's gaining a lot of traction, it's got Google behind it. Google have clearly bought the experience from Borg, etc. It already includes several advanced features, but it does require, it may require changing the application to get to running Kubernetes, and does require understanding a bunch of new concepts. And that's it, I think. Yeah. So now you can understand why I didn't add Nomad, because that would have been a long talk. But are there any questions?
Do you performance test any of these solutions?
No. I would like to mention, did you see Jeff Nikoloff's post? So Jeff Nikoloff did Docker published this thing recently about how fast Swarm was and how slow Kubernetes was. But there was a bit of a funny post, because what they did was they said, Swarm starts 1,000 nodes quicker than, I can't remember how many, 10,000 nodes, much quicker than Kubernetes. But they weren't really comparing apples with apples, because what they'd done is they'd done Docker run, Docker run, Docker run, Docker run. But they'd done like kubectl apply, kubectl apply, kubectl apply, and that's not what you do with Kubernetes. As we saw there, with Kubernetes you do a replication controller and set the scaling. So although Docker run was faster than kubectl apply, it was much slower than the replication controller. So I thought it was a bit disingenuous of them to claim that Swarm was much faster than Kubernetes. Also Nomad just published some results and claiming they were much faster. I don't know how interesting it is to like launch 1,000 containers in a minute. I mean, what does that tell you? It's interesting for some applications. For example, if I don't know, you can. I mean, I think most people looking at these things are talking about doing long-running services that are going to start and stop containers, at a much lower rate. But you may, like for instance, use your containers for computation, like in high-performance computing thing, for I don't know, running like financial analysis or physics simulations. In which case, you may want to start 1,000 containers in a second.
If someone wants to run, or would be inclined to run, if someone would be inclined to run multiple processes in the same container, is it better to run multiple processes within the same container, or is it better to use something else to start multiple containers with multiple processes, or am I asking it wrong? And can you enlighten us?
So I think so there's sometimes sort of an argument that people say you should have one process per container, but it's really just a rule of thumb. So you probably want to like separate your database from your application, keep those in separate containers. If you run multiple processes in a container, that's fine, but you do have to be a bit careful at managing them. So like signals get proxied correctly, in which case you want to use what are the names of them? There's a few, like init things you can use to do that. Does that make sense? Does that answer your question?
That's fine.
Okay.
Thank you.
There's a Kubernetes framework for Mesos. Could you think of a reason to use that instead of using either?
Yeah, I mean, so Kubernetes gives you a bunch of different ways of doing things, right? You've got your replication controls and so on. So if you've already got an existing infrastructure running different things, you can just plonk Kubernetes on top of that and play with it. So I guess that's the idea. I'm not really sure. It's an interesting idea, though. Anybody else? I think everybody's typing. Go on.
Yeah. Does any of these frameworks provide oversubscription, where you kill processes because others have higher priority or you lack resources?
I know Mesos is working on that. I'm not quite sure where it is. I think Kubernetes is working on it, but that's definitely not there yet. Swarm doesn't even have that concept, really.
Lol.
Like if you're using spread, you can just start as many containers as you like and it'll just crash eventually.
You can see they're running on a virtualization platform that does oversubscription.
Yeah. But then it doesn't kill the lower priority.
Yeah, no, Mesos is definitely working on that though.
Okay.
Okay? Thank you.